या कोई बात नहीं. Javed, you make trust Otto a co-host, okay? Yeah, it's okay. Now he can share the screen. Okay. Okay. Yeah. So, just a minute. Okay, fine. So I suppose we can start today's seminar. So good afternoon, everyone. Welcome to the today's astrophysical seminar. We are happy to have Otto Trust with us. And he's a PhD student at Mbarara University of Science and Technology, Uganda. And he's working under the supervision of Professor Edward Jirura, Dr. Santosh Joshi from Aries, and Dr. D. Cat Peter from Royal Observatory of Belgium. So today he will be talking about on evaluating the origin of chemical anomalies in AM stars. So Otto, please go ahead. And you have 45 minutes for presentation. I will remind you after 40 minutes. Okay. Yeah, please go ahead and unmute yourself and start. Your screen sharing is disabled. First, you have to start screen sharing again.
Okay.
Yeah, we can see now.
Hello, everyone. Yeah, I'm Trust Otto, as introduced me, PhD student under supervision of Prof. Edward Jirua, Dr. Santosh, and Peter Dikat. The topic of the thesis is evaluating the origin of chemical anomalies in AM stars. Within the intermediate mass stars on the main sequence, there are a number of interesting phenomena which were observed there, such as the chemical peculiarities, pulsations, and activity, which are very interesting. So particularly the CP stars, those are the chemically peculiar stars. They are those whose abundances deviate from the normal. The normal stars are those which have solar abundances. So the CP stars have deviating absorption lines in their spectra. The weak lines tend to be weak, while the metal lines are enhanced. This is thought to be as a result of atomic diffusion, where the light elements drift towards the core and the heavy elements drift towards the surface under radiative acceleration. So this atomic diffusion is facilitated by calm environment, which can be caused by maybe the magnetic field, and without mixing. Mixing can be created by convective nature of the material, or meridional saturation caused by rotation or pulsation. Yeah, so rotation becomes a very vital process in these stars. So it needs to be constrained properly. Good enough, there are space missions which have provided the high precision data, which is even almost continuous for a long period of time, such as Kepler, K2, and TESS. So with this data, rotation has been constrained at least to some good level based on splitting of the pulsations when present. Then using meridional saturation, using modulation in the presence of spots. Barona analyzed a number of them, very many of them, of the A stars based on modulation, and was able to obtain the rotational period, and they found some stars which were having this feature in their spectra. So they interpreted this as the rotational frequency, but they failed to interpret this, the hump. Then later, SIO 2018 compared the visibility spectrum of these stars with the models of the Rossby waves, and realized that the hump is actually the Rossby waves, while the spike is the rotation frequency. And then they named these stars the hump and spike stars, which are now the major group of stars under this study. Yeah, so previously there was a survey which was started in 2000, searching for variability in AP and AM stars under mainly India and South Africa. Then later, scientists from other countries joined this survey. It has been very successful. Very many papers have been published. Actually, even recently, one has been accepted this year under MUNRAS. Now, because of the success of this survey and the discovery of the hump and spike stars, we were motivated to start a collaborative group under these three countries. So the problem of this study is mainly failure of the atomic diffusion process to exhaustively explain the chemical peculiarity of AM stars. Yeah, we see that making progress in solving this issue, it can be done by, first of all, getting precise values of the rotation properties and the spots if present. Then also determine the parameters precisely using high resolution spectra, and then perform an evaluation of the processes suspected to contribute to the chemical peculiarity using MESA evolutionary code, because it is freely available and it is robust, it is good. So the aim of this study is to evaluate the transport processes behind the peculiarity of these stars. And to achieve that, these objectives have to be achieved. Look at the rotation properties, then the characteristics of the sample, so that we are sure the AM stars themselves and their parameters, then evaluate the processes. This study is important because it influences the evolutionary models, and also adds to the overall number of AM stars some new AM stars. Then it also locates them in the Echelle diagram. This study focuses on AM stars and A stars, which have hump and spike features in their spectra. And only those which were observed under the main Kepler mission. So we obtained them from these studies, Barona 2013, 2015, and Gray 2016. So we managed to obtain 170 of them, of which 131 are suspected to be normal and 39 are AM. So we downloaded the data, Kepler data, from the MAST website and selected the PDC flux. PDC flux is that flux which was obtained by fitting the SAP flux, but SAP flux has some errors, some artifacts, some outliers. So they were removed or they were reduced by fitting with the polynomial to produce the PDC flux. So we chose the PDC flux because it is good enough for this study. Then we stringed together all the data for all the quarters, because these data have around 18 quarters. Then to cater for the differences in the flux, because when you join them together directly, you find that there is overlap in the flux. So that was removed by only getting the difference in flux. So they were maintained at the same level, then stringed together to produce one light curve. Then that light curve was analyzed and then produced a Fourier transform of it. To produce the Fourier transform, we used the period of 4, and we were able to obtain what we see in the figure. So the green shows the previous estimate of the rotation frequency, while the one in the middle, it shows the rotation frequency of this study. And then the last panel shows its harmonic. You can see there is a difference, and this difference is significant. So we compared the previous rotation frequency with the frequencies in this study, and the targets which are within these enclosed ellipses, they are those whose values are very different. In other words, whose values have been improved very significantly. And also the amplitude, of course, it was also affected. And it is important because we are going to use it to constrain the spot size. Then we compared the rotational velocity, because from the rotational frequency, we are able to constrain the rotational velocities. These are estimated to be the equatorial rotational velocities. Then compared with them with those which are available in the literature, that is V sin I. V sin I is the projected rotational velocity. It is like the maximum, the minimum. Yeah, so when we compared them, as we can see in this figure, all the stars fall in the reality region, The blue dashed line represents inclination angle of 90 degrees, which means at that moment, the projected rotational velocity is the same as the equatorial rotational velocity. Yeah, so this one is a good sign because it shows that the rotation period, the rotation velocities we obtained from the spike are good. Then comparing for AM and the normal A, as expected, the rotational velocities for AM, the average is lower than, the average for AM is lower than that of normal A because AM stars are expected to rotate more slowly compared to normal A, because that is what actually facilitates the diffusion. Yeah, so out of the 170, only a few were compared because they are the ones that have a V sin I in the literature. Others don't have, mainly because their V magnitude is high. So what I mean is that they are faint. They cannot be observed from ground to produce sufficient spectra for analysis. Then we obtain the magnitude of the spike. That magnitude is suspected to be, the amplitude is suspected to be related to the spot size. So we compared it with a transiting exoplanet. So we borrowed the idea and estimated the radius of the spot using this relation, where this temperature is the background temperature, and this one is the temperature of the spot, which are believed to be different, slightly different, by up to even 1000 Kelvin. So that ratio was used to estimate radius values which are a bit realistic. So comparing the spot size for normal and A, the distribution seems to be the same. And these are the average values. So from these values, we see that the spot is small, just approximately 1 Earth radius. So as big as the Earth, they are small. Then to confirm the presence of the spots, because when the spot is there within the light curve, it will create some signal within the light curve. So we had to search for that signal by performing an autocorrelation of the light curve. Autocorrelation, that is comparing the light curve with itself at a given time lag. When the time lag is 0, it means at that moment they are exactly the same, and the autocorrelation is expected to be 1. So we did that and performed the autocorrelation for these stars and produced some like this one. This is an example of the autocorrelation. Now this autocorrelation function mimics an underdamped simple harmonic oscillator whose relation is this. So which means fitting the autocorrelation function with this model, one can be able to estimate this decay time scale. This decay time scale can give us a picture of the time taken for the spot to increase and decrease. And also from this, we get the period, the rotation period from the autocorrelation function. Yeah, so in this figure, we see there is it is not the maximum, but in the middle of the period. So the period of this stuff from autocorrelation is this one here. But between half the period, there is another peak, which indicates that for this star, there are other spots which are diametrically opposite, but of different strength. That is how it can be interpreted. Other autocorrelation functions are given here. So we were able to obtain the period of rotation and also the decay time scale from such. However, some of the light curves, about 40%, did not produce any maxima, which shows that the light curve was not similar. There is no signal produced, which shows that possibly the spots are weak in such stars and the signal is weak, and it is taken within the noise. Yeah. So which means the strong spots are not necessary to produce the spike, because these stars have the spikes. So we compared the periods, those produced from autocorrelation and those obtained directly from the Fourier transform, and realized the majority are well correlated, they are very close. While these two, there is a big difference. And this is because the dominant frequency in the Fourier transform is not the spike. So for all the stars which would deviate from this line, the dominant frequency in the Fourier transform is not the spike. So the previous methods, whereby they were considering the dominant frequency to be the rotation frequency, I think this is where the problem was coming from. Dominant frequency, which is not the spike. So where the spike is the dominant frequency, it is by coincidence that it turned out right. So we tried to compare different parameters, the rotational properties and the properties of the spots, excuse me, with the atmospheric parameters, that is effective temperature, log G, and luminosity. We only found some good relationship between the rotation velocity and effective temperature. And I think that is not new. And also, yeah, that is the same. And luminosity. We tried to get the relationship between the decay time scale of the spots and the radius, and the correlation is not strong. Then we presented these stars in the Echelle diagram and trying to see the influence of these properties on the Echelle diagram. From this first panel, we can see that the rotation frequency increases as one ascends the main sequence. Even here, As one ascends the main sequence, the rotational velocity increases, and I think that is not, that is also expected. Then from here, as one moves away from the zero edge main sequence, as the stars evolve, the radius of the spot increases from here. Here there is nothing much of a trend, and even here. So from this photometric investigation, a paper was published. We are going to see details after. So in a sample of 170, we got those which were brighter than 10.5 magnitude, and again those which were not known to be binaries. We wrote a proposal for observation under HERMES, which went through, and 12 of them were observed on the nights of 2nd, 6th, and 7th November 2018. HERMES is a very good spectrograph, produces spectra with very high resolution, 85,000, and it is very stable in terms of radial velocity. The spectra were passed through the dedicated pipeline, which includes removing the bias, the stray light, and also calibration of the frames. Then we performed normalization, and these spectra were already corrected for the barycentric motion. So before we obtain the parameters of the subsample of 12 of 9 of them, 9 stars, we performed the spectral classification because at least it gives a clue of what is going on. We used the 2 data sets. The first one was the spectral energy distribution. Yeah, so spectral energy distribution, we compared the template libraries like Echelle 2017 with those for these stars and obtained these spectrotypes. For example, this one, it is an F2 dwarf. In this case, dwarf means the main sequence, while giant, it means it has evolved off the main sequence. So using that criterion, we found one red giant. Then we performed classification again using HERMES spectra. The HERMES spectra is high resolution, and also we're supposed to compare those spectra with the spectra of the standard stars, but we were not able to obtain a spectra of the standard stars using the same spectrograph HERMES, so that we can create a grid and compare them. So we decided to use the available libraries, and those which are available, they were observed with a different spectrograph, which are even low resolution, and also the wavelength range is between 380 nanometers to 560 nanometers. So we have to process the HERMES spectra to suit the characteristics of the available spectra for the standard libraries. So We reduced the resolution, rebinned the sample, and truncated the spectra to make sure that they are the same characteristics. So for HERMES, we determined the spectral type from 3 main regions. That is the calcium K line, then the hydrogen lines, and that is H gamma and H sigma, then also from the metal lines. For the AM stars, those 3 different regions, they give different spectral types. While for the normal stars, they give the same spectral type. So the first star is actually an AM star based on this method, because the calcium K line gave us A2 spectral type, hydrogen lines gave us F0, while the metal lines gave us F3. These are different spectral types, making it a classical AM star. It is classical because the difference between the spectral type from the calcium K line and the metal lines is more than 5 subtypes. Otherwise, if they were less, it would be a marginal AM star. Yeah, so even this one turned out AM. So from there, we're supposed to now get the atmospheric parameters. We use the traditional method, that is spectroscopy. But to do that well, one needs the initial guess, and we did that from photometry and SED. These are the databases we used, and this is the fit for the spectral energy distribution for these stars. We obtained the initial guess and used that initial guess in the analysis of the spectra. So first, we obtained the radial velocity by cross-correlation technique using the iSpec. Then we obtained the V sin I using the Galfit. Galfit is a private code by Fremont. And we considered different regions of the spectra, because different regions respond differently to different parameters. Like the hydrogen lines, they give good estimates for log G and T effective. So for V sin I, we used the magnesium triplet. Then for stars whose temperature is less than 8,000, we obtain the T effective from the hydrogen lines, and the log G from the ion lines, while those whose effective temperature is more, log G was obtained from the hydrogen lines, but the effective temperature was obtained from a region which is having more metal lines. That is, it was between around 510 to around 620, that region of the spectrum. So we divide the spectrum into small subregions and fitted them, then obtain the effective temperature for each, and then got the average. So this is the final fit. The red is the synthetic spectra, while the black is the observed spectra. We compared the atmospheric parameters, effective temperature and log G, with those which are available in the literature, especially available for all the stars analyzed. And we found some good correlation. Then we obtained the abundances using synth and the binmag. Those are the ideal routine. So for each spectrum, we divided it into segments of around 5 nanometers, then analyzed the abundance in each, then go to the average for each element. Yeah, so the abundances obtained were compared with the solar abundances, and we were able to produce such a plot. Then the gray region shows the elements which were vital in the classification. As we can see in this first figure, the calcium and scandium abundances are low, while the iron peak elements, the abundances are high, and also the rare earth elements, they are high, indicative of AM characteristics. While this one, generally they are solar, and these ones we see they are also overabundant, which also shows AM characteristics. And these same characteristics were also captured in the classification, which gives confidence because it has been captured using 2 different methods. So for the sample we studied, only 2 stars have abundances already determined in the literature, and we compared them and found a very good correlation. We also presented these stars in the Echelle diagram, and to do that we had to obtain the luminosity, which was obtained from the standard technique or using parallax. We used the Gaia parallax, Gaia data release 2. By then, that is what was available, which was the best at the time. Currently, there is Gaia data release 3, but for us, we use data release 2. Comparing the results with the previous ones, there is a good relationship. The radius was obtained using this Stefan's law. From the HR diagram, one is a giant, and it is seen from here, also from the classification from SED and the HERMES, because the luminosity class was a 3, and it was shown as a giant from SED. Then this one is a marginal AM. So from here we see AM stars. Yes, the sample is small, but their temperature is lower compared to the normal ones. And all the AM are within the Delta Scuti observational instability strip by Murphy 2019. So the spectroscopic.
You have 5 minutes left.
Okay, thank you. So the analysis, which is spectroscopic, the results are also presented in a paper. So to proceed with evaluating the transport processes, we needed the mass and age, which are obtained by fitting evolution tracks and isochrones. And then we activated the conditions, transport processes, radiative acceleration, turbulence, and the thermohaline convection. We also accounted for rotation. We did not account for magnetic fields because the AM stars, the magnetic field is low. Then we did not account for mass loss. These stars are mainly on the main sequence. And we evolved these stars from pre-main sequence up to the age we obtained. We considered only these elements. The reason being those are the ones which are also in the opal opacity library. So, and that is where radiative acceleration is activated. It is a requirement. So those are the results. About 2/3 of the elements agree for the observed and the predicted. So these are the conclusions from the start. We see that rotation can be well constrained using the hump and spike feature. Then the spots which are there are small, they are weak, they are short-lived. In case the magnetic field is present, it is also suspected to be weak. Then we were able to characterize, we obtained the 2 AM stars, 1 marginal AM star, and 6 normal targets. Then 2/3 of the elements in common agree, and the agreement is best for the heavy elements. So we suspect that these processes take part in influences the chemical peculiarity in these stars. However, not all of them agreed, which implies that there could be some other processes at play, but they are still unknown. Yeah, so these conclusions were based on statistically a few stars. So it could be important to study more stars of this kind and also use more elements in the comparison. Then we are going to look at K2 and TESS and also other spectrographs like that attached to DOT, so that we can make good follow-up studies to improve these results. These are the publications that we obtained from this thesis so far. Acknowledgements to my supervisors, then the sponsors, ISP, the data, Dr. Patricia, Professor Don Katz, Vadim Premat for the code. I can't pronounce this name, but he helped me so much in MESA. He's from University of Wrocław, Poland. Then the hospitality I received from Aries when I came in 2019, and also the computing facility to run MESA, because MESA is stubborn, it needs high tech. My family, then the Department of Physics must. Thank you for listening.
Okay, thank you, Otto, for the nice talk and keeping up with time. So now the floor is open for question. Please unmute yourself or raise your hands so that yeah, I can call your name. Yeah, so we have one question from Patricia Lempens from Royal Observatory of Belgium. Patricia, please unmute yourself and ask a question.
Okay, hello everyone. Can you hear me, Otto?
Yes, Patricia.
Hello, Otto. Very nice presentation. I liked it very much. I followed all of your explanations very clearly, and I really liked it. I have, if I may, I have a couple of questions. I have one. I will come back to that. I would like to see your slide with the final results again, because I think the conclusions came a little bit fast. So I would like to see your final result where you compare with the models. But I have a first question, if I may. My first question is, when you evaluate the spike and the rotational frequency with the autocorrelation method, what would happen, Otto, if instead of spots, you would have stellar pulsation going on the surface of these stars? So what would the method of ACF, autocorrelation, give you if you would see pulsation instead of having spots?
Actually, I asked myself that question this morning because the autocorrelation searches for the signal in the time series. So if there is a pulsation, which is also a signal, I think the autocorrelation will also be there showing those maximum and minimum, because there is a signal, though I have not tried to look at a light curve where there is pulsation.
Okay, I understand. I think I agree with you that you may have some signals with auto cross correlation as well if you have pulsation. Okay, and then my second question, if I may, I would like very much, in fact, to see the slide where you finished your results, because it was the slide, I think, where you show that there is some modeling ongoing and where you show which methods can explain the chemical peculiarity. And it was a little bit too fast for me and maybe for the others to see. Thank you very much.
Yes, thank you. This one.
Yes, this one. Yeah. So can you repeat your conclusions with respect to the models that you have? Which models are working and which ones are not working?
Yeah, so the blue shows the gray shows the observed, while the blue shows those from Richer, and this one is where turbulence is activated, the blue. The cyan shows where radiative acceleration is activated, while the red is where thermohaline convection is activated. All these are activated together with the pure diffusion and rotation.
Because you included rotation as well in the modeling.
Yes.
Okay, but here you show that, I mean, does rotation is also included in the models by Richer et al. Or not?
No, it's not.
Okay,
yes.
I see. Okay, thank you very much. Thank you, Otto.
Okay, thank you.
Thank you, Patricia, for your question. So next question is by Tatiana. Please unmute yourself and go ahead.
Okay, just hello to everybody. Did you hear me?
Hello.
Do you hear me?
Yes.
Okay, I have at least 3 questions. First, so according to your photometric analysis, there is practically no difference between the normal and AM stars, isn't it? because the amplitudes in one case is 19 ppm and in other cases 21 plus minus 2. So it is the same.
Yes.
Photometrically, these stars are not distinguishable. This is my first remark. I don't know how to explain, etc., but you have somehow to explain it. And the second question, did you, maybe I miss it, but did you find some difference between the microturbulence velocities in AM and A normal A stars?
Microturbulence for AM is slightly more higher than that of normal A.
How slightly? Because usually in the literature, these stars have, in particular, in the temperature region between 7 and 900, or 7 and 8,000 kelvins, they have maybe 2-3 times higher microturbulent velocities AM than the normal A. In normal A, it is 1.5 and AM in 4.5, etc. Did you find the same in your, according to your spectroscopy?
According to spectroscopy, they are 2.5, let me confirm, around 2.7 and above for AM.
And 2.5 for normal?
For AM.
Yes, for AM, 2.7.
And above. Yes, 2.7 and above.
But in
around
principle,
2.
Okay. And they just want in the richer modeling, I think that they include the both because they consider the diffusion, isn't it?
Yes.
This is a diffusion models, and they include both the levitation, radiation acceleration, and gravity settling. So I don't see why
Yes.
you put the models only with some levitation.
Sorry?
But the models only with the levitation are not in principle cannot be included, because without gravitational settling, it is nothing. The star always have the balance in the atmosphere. There should be considered the balance between the gravitation and radiation.
Yes,
between the gravity and
because
radiation. So the blue, the cyan lines, the cyan dots are nonsense from my point of view.
no, the details are like that radiative acceleration in addition to diffusion. Diffusion is there for all.
The diffusion includes the acceleration, the radiative acceleration. Diffusion includes
with MESA, you can deactivate radiative acceleration. Actually, radiative acceleration is only performed for a few elements in MESA. Very few elements.
But
actually, ion.
It is nonsense. For me, it is nonsense. Okay, thank you.
Okay.
Okay, thank you for your question. Are there any further question clarifications for Otto? Yeah, Aruna, please go ahead.
Hi, Otto. This is Aruna here.
Hi, Aruna.
Yeah, it's a very nice talk.
Thank you.
Yeah, I really enjoyed your talk. And I have just one small question. The slide that is being shown here, you have mentioned that these discrepancies can be, can also imply that it may be because of some other processes. Now, do you have any processes in mind, like which can be the, which can affect, because these abundances they do not match here with these particular models that you're showing?
No, actually, I stated that the other unknown processes.
Okay, so these processes are still unknown. Okay, fine. I have one more question. Like in your slide 12, you had mentioned that the average rotational velocities for AM and A stars. Okay, 150 and 161 average velocities. Now, I just want to know the range. Range of velocities for AM stars and range of velocities for A stars. I think that was a slide number 12.
This one.
Yeah, that 105 and 161, these are the average rotational velocities. What is the range? You don't have the numbers? Okay.
Yeah, I don't have the numbers now.
Okay, doesn't matter. Maybe when you get them, it's okay. I just wanted to know if there is an overlap, and then if there is an overlap.
Yeah, the overlap is there. The overlap is there.
Okay. So if there is an overlap, then how this information can be used to distinguish this? That was my actually the question. But yeah, later on, maybe I can find, you can tell me the range. Yeah. Thanks
the
again.
overlap is there.
Yeah.
Thank you.
Yeah, very good talk. Thank you.
Okay, thank you, Aruna. Are there any further questions for Otto? Yeah, Patricia, you want to ask something because I see you raised your hand again.
If I may?
Yeah, sure. Please go ahead.
Okay, I have one more question for Otto. I understand that you have classified the stars AM versus normal with respect to degraded HERMES spectra, because you didn't have the HERMES spectrum of a standard star, which has also, let's say, well, underabundance or overabundance like a standard AM type star. Now, if you would have such a spectrum of a good resolution HERMES spectrum of a standard AM, known AM type star, do you think would it be worthwhile to redo that classification? Would you do that? Would it be, could it give a better result maybe?
Possibly. I think it would be good to repeat the study with the high resolution HERMES spectra for the library.
Because you had to degrade the spectrum by how much? Do you remember?
Because the other one, the resolution is around the 5,000. 5,000, while the HERMES is 85. So HERMES is too high.
Wow. So you had to degrade a lot in order to do the classification. Yeah.
Yes.
Okay, I see. It would be interesting to have a good HERMES spectrum of several standard AM type stars, which are well known. Yeah. It would be worthwhile. Okay, thank you very much.
Thank you, Patricia.
And yeah, see you all next week.
Okay, thank you.